Right, here we are again. So, before we start, can you get your notes open at page 188, and can you also get your blue workbook out ready so that you can do your retrieval roulette? Okay. So here's your retrieval roulette for today. So answer this in your blue workbook, pause the video to answer the questions, and then replay once you have it done. So pause now. Okay, so here's your answers. Question 6 was drawn a diagram. I will show you that in just a second. So again, pause, mark and correct, and then I'll give you question 6. Okay, so for 6 then, it was to draw the diagram to investigate the relationship between the length, the length of wire and the resistance. So if you remember, this is the one we did in Mrs. Turner's room when I actually burnt the wire, if you remember that. So a couple of important points here. Always label anything that isn't a proper circuit symbol. So the meter stick here I have labelled, I forgot to do my wee scale on it, and the wire. So you're going to have an ammeter and a voltmeter so that you can measure the current and the voltage and then calculate the resistance. You're going to have a meter rule or something like that so that you're actually measuring the length of the wire. And remember, wee arrows like this just show that these connections are variable, so they can move around. Okay. So just before we get on to today's work, I just want you to spend a little bit of time and remind yourself about those equations that we learnt just before Christmas there. So this was at the start of the electricity in the home topic. So if you look back at, this is page 177, electrical work and power, we learnt these different equations. So work done is equal to the charge multiplied by the potential difference or the voltage. And remember, because work done is equal to energy transferred, then that means this can be written like this. And I will use both of these equations. It just depends what the question's asking for. If the question uses work done, I tend to use W. If it uses energy transferred, I tend to use E. Another thing then that we did was, because earlier on in this topic we learned that Q was equal to IT, so current multiplied by time, then all we've done here is replace this Q in the equation with IT. So we end up with W equals ITV. And this one here just allows us to sometimes do questions all in one step, as opposed to doing two different separate calculations. Okay. Over the page then on 178, another couple of equations. So this was the power equation that we learnt in year 11. So power is work done divided by time taken, or again, because work done is equal to energy transferred, power is equal to energy transferred divided by time. And that is still useful in this topic sometimes. However, then we went on and showed, and you can look back over your notes on this, that P equals IV. So the electrical power is equal to current multiplied by voltage, and then substituting in, there's all the work over there for that, substituting in using V equals IR, we can end up with these other two versions. Now I will have said at the time, strictly speaking, you don't need to learn these ones off by heart. You do need to learn this one. You'll always be able to figure these ones out as long as your algebra's up to it and you can substitute in for these, then you'll always be able to figure them out. I've got to the stage now, because I use them so often, that I do remember them, but as I say, it's not essential. And together these are known as Joule's law. Then, if you remember, we did approximately 1 million questions on that stuff. So if you need to, look back over those questions and your solutions to make sure that you're on top of all of that. Right, so now we can finally get on to what we're learning today. So we're going to start looking today at the cost of electricity. Now, this is quite annoying, because I have spent our entire time together as a class going on at you about how energy always has to be in joules in equations. Whenever we're dealing with the cost of electricity, we use different units. Annoying. So just if you think about that power equation, so power is energy divided by time, or we can say energy is power multiplied by time if I just rearrange that. Because of this, then the amount of energy that gets transferred, the amount of electrical energy that gets transferred to something is going to depend both on the power of the device and the time that it's left on for. So if you have a really powerful, like a really high wattage appliance, and it's on for ages and ages and ages, you're going to transfer a lot of energy. If you have a really high power and it's not on for very long, then you might end up transferring the same amount of energy as something which is a really low power but is on for a really long time. So the energy transfer depends on both the power and the time that it is switched on for. Now, a couple of different things we need to get used to here. The energy we're used to being measured in joules, but as I say, in this, my dog is barking, hold on 1 second. No idea what he was parking at, sorry. So anyway, what was I saying? Yeah, so the energy we use here, the unit we use here for energy is kilowatt hours, right? So kilowatts you will be familiar with. Do you remember power we've always measured in watts? So look, if you look up here, power, if we now have that in kilowatts and we have our time in hours, then that means our energy will come out in kilowatt hours because we've literally multiplied kilowatts by hours. So that's just where that comes from. Just to add further confusion in the world of household electricity, people tend to talk in the terminology of units. So 1 unit is just 1 kilowatt hour. So like whenever your electrical readings are being taken, they will see how many units that you have used. That's just how many kilowatt hours that you've used. So just down here, we're just going to be writing in what we were talking about up here with the units like the kilowatt hours and all that. So energy transferred in kilowatt hours is going to be equal to the power in kilowatts multiplied by the time in hours. Another way that can be worded would be the number of units, because remember 1 unit is 1 kilowatt hour. So the number of units is equal to the power multiplied by time, power in kilowatts and time in hours. So pause and get that written in. So just underneath that then, there's a couple of little notes on the units, so the stuff I have been blethering about there. So remember power is in kilowatts instead of watts like we're used to. Just a reminder, if you're going from kilowatts to watts, then you are going to, or sorry, other way around, if you're going from watts to kilowatts, then divide by 1,000. So 2,000 watts would be 2 kilowatts. Hopefully we're all okay with that now. Another thing is to note that time's measured in hours. So to convert from seconds to hours, you divide by 3,600. So the reason for that is that to go from seconds to minutes, because there's 60 seconds in a minute, you would divide by 60, and then to go from minutes to hours, you would divide by 60 again. So that's the same as dividing by 3,600. I tend to do this more often, like dividing by 60 twice, but everyone prefers different things. So for example, 1,800 seconds divided by 3,600 is half an hour. One wee bit to fill in down here, changing 1 kilowatt hour into joules, just in case they ask you to do that. For some reason I doubt myself on this one all the time. So the way I tend to always do it is I just go energy equals power multiplied by time. So normally whenever I'm substituting numbers into equations I don't put the units on, but I do in this one just to keep myself right. So if we have 1 kilowatt hour, that's like 1 kilowatt multiplied by 1 hour, right? Which is 1 kilowatt is 1,000 watts multiplied by 1 hour is 3,600 seconds. And then if you remember, energy equals power multiplied by time. So if we have our power in watts and our time in seconds, that's the units that we're already used to. Our energy will be in joules if that's the situation. So that's why I have done that. So that gets me that many joules. Okay. So over the page on 189, then we're going to start figuring out how we get the actual cost. So all that stuff that we were looking at there was just really to figure out the amount of energy that was being used by an appliance, or the number of units that was being used. So we're going to now transfer that into the actual cost. So here's our equations for that. Pretty self-explanatory. If you know the number of units that are being used and you know the cost for 1 unit, you can work out the cost of using an appliance for a certain amount of time. So the cost, number of units used multiplied by the cost per unit, or a sneaky wee one which is useful in some questions Because the number of units is just the energy that's being transferred, we can rewrite that as power multiplied by time, and then you just have to multiply that by the cost per unit. Just a reminder, not our usual units for these things, so kilowatts and hours there. So get those written in for me, thank you. Now the way this tends to come up in past paper questions will be they'll give you like a ripped up bit of a bill, and then they'll say, oh my goodness, look, this actual final cost has been ripped out, can you figure out what it is? Or some other wee bits will be missing and you might have to work backwards. So let's have a little look at this one. So we've been given this electricity bill and we have to show where this £223.05 came from. Oh, here, I forgot to say whenever we were up here, be very, very careful, because what tends to happen is that the cost per unit will be given to you in pence, and then see the way the final answer here is in pounds. So you always have to be super careful and take note of whether you're working in pence or pounds and adjust accordingly. So if we look at this, the present meter reading, so do you know the way the guy comes out to your house and takes a meter reading, and you just give him a number? Sometimes if you're there, you'll give him the number, or if you're not in, you'll have to fill out a wee form with it on, or you can enter it online as well. So the present meter reading, you just go and you look at your meter and it'll have a big number. So the present meter reading is 57,139. Then they'll have the previous meter reading. So this was what was read the last time that your meter was read. The units used then is going to be the difference between these two numbers. So between your last bill and this bill, you've used this many units. So if you take this away from that, that's how many units you have used since the last bill. And then it gives you the cost per unit, and then the actual bill cost, the 223.05. So we've been asked to show where this comes from. So if any of these numbers were missing, that's like an example of the question. So the number of units used is going to be the present meter reading, take away the previous meter reading, and that's where that 1487 has come from. Okay. Oh. Then to get the cost, it's going to be the number of units used, this equation that was up further on up the page. So the number of units used is the 1487 multiplied by the cost per unit, which was 15p, gets 223.05 pence, which then we have to convert into pounds, 223.05. Okay, so that's what I mean, just be careful with pounds and pence. Right, another little section here about switches. So this one here is fairly self-explanatory. It's just a regular switch, and this is what is going on inside it. So if you have this little connection that isn't connected, then whenever you press the switch down, it's going to push these together and allow the current to flow. So this would be our closed switch and this would be our open switch, and that's as straightforward as that. That's all that's going on. So let me see if there's anything else in the notes I've forgotten. So this type of switch acts as a make or break. Yeah, see, forgot about that. So it either makes the circuit by completing it or breaks the circuit by putting this little gap in the circuit. And then that's going to turn it on or off. So when the switch is open, there's air between the conducting contacts. Air is an insulator, so no current flows, but when the rocker, like the bit you actually press, is pressed, the conducting contacts are pushed together, forming a complete circuit so current can flow. So easy peasy question, why is the rocker made of plastic? I don't think I've actually written this very well, but obviously plastic is an insulator, and that is the bit we touch it. We do not want electrical current to pass to us, so we don't want to be electrocuted. So anything that we touch should be made out of an insulator. So get that written in. Now, on page 191, this is such a simple little thing, but so clever. So most of you probably have in your house a bulb, like at the top of your stairs or at the bottom of your stairs, that you can turn off from either the top or the bottom. So this here is how it works, and it is really clever. As I say, really simple, much more simple than you would think, but it is very, very clever. So let's have a little look at this here. So see the way this currently is. If we follow the circuit round, then we have a complete circuit. So that bulb is going to be on. So say you're at the top of the stairs and you want to turn the bulb off, then you would flick the switch, and you're going to flick that from here to here, which means that you're no longer going to have a complete circuit anymore, because it's going to come along here and down here, and then it's not combined there. Then say you go down the stairs and you want to turn the light back on again, right? So this one would be connected here, then you're going to flick the switch here, and now they're connected again. So it is really, really straightforward, but really clever. I actually really like in the classroom building a wee model of this to show, because it helps show it, but we can't do that. There's a wee diagram down the bottom which shows what I have been pointing at there a little bit clearer. So if we'll have a look at this. So here's our two switches, one at the top of the stairs and one at the bottom of the stairs. Currently, this bulb is on because we have a complete circuit. Then this switch here is pressed, so we don't have a complete circuit anymore. We've got a gap in the circuit, so the bulb's going to go off. Then if we turn this one on, now we have a complete circuit again. And then what's happened from here to here, this one here has been pressed again and it's incomplete. So it just means that whenever you press the switch, you're always going to be changing the current situation. You're either going to be making the circuit, or you're going to be breaking the circuit. And if you notice down at the bottom here, you do need to be able to draw this circuit diagram. Just draw it like this. So you just have two wee straight lines, and then your switches, which can move either way. Okay, page 192 for the last little bit for today. If you remember, just before Christmas, we actually got a go at wiring a plug. So you do need to be able to label all the different wires. So very quick reminder here, inside your plug you've got three wires. You've got the live wire, which the electricity goes in on. You have got your neutral wire, and you have your earth wire. So the live wire is always connected to the fuse, and next lesson we're going to be looking at fuses in a little bit more detail, but that's really a safety feature, because if a big surge of current flows in your live wire, then it's going to break that fuse, which is much cheaper and easier to replace than replacing your whole appliance, which could break. The earth wire, oh sorry, I didn't even say there, the live wire is brown. The earth wire is like a green and yellow stripy wire. It always goes up to the top into that longer pin, and then the neutral wire goes into the one that's left, which is blue. Okay, so do spend a little bit of time reading back over that page 192 for me, just to get that back into your head, because what you're going to do for me now are the questions on page 193. So if you answer those questions for me, you can either answer them on this page, I think there's just about enough room to write it in, or on your blue workbook. Okay, that is us for today. I'll be asking to see your answers to these, and I'll see you next day. Bye.